Now see the quantum mechanical treatment for one-dimensional harmonic oscillator. So this a QM treatment. We have known the Schrodinger's equation is a d to psi by a dx square plus 2m by h bar square e minus v psi is equal to 0 is a general Schrodinger's equation. Now the V for one-dimensional harmonic oscillator is 1/2 a kx square, and therefore this d to psi by a dx square plus 2m by h bar square e minus 1/2 a kx square psi is equal to 0. To solve this equation and for simplicity we introduce a zeta is equal to alpha of x, and this zeta is a dimensionless quantity, and therefore this x is equal to is a zeta by alpha, and x square is equal to zeta square by alpha. So we require here, and from that d zeta by dx is equal to alpha. Now we are going to find out the value of the d to psi by dx square in terms of a d zeta function, and therefore here a d zeta by a dx d psi by a dx is equal to purposefully we are taking this one as is equal to a d psi by a d zeta into d zeta by dx. Okay, so this d zeta by dx is nothing but alpha, and therefore this is the alpha dou psi by dou zeta is equal to d psi by a dx. Now again d to psi by a dx square is equal to a d by dx of alpha dou psi by dou zeta. So this can be solved as d zeta by dx into dx by is equal to d by dt of okay. So this d zeta by dx solve, and dx by d zeta of this alpha d psi by d zeta is equal to after solving this we get this alpha square d to psi by d zeta square. That means this value of this d to psi by d square is d to psi by d zeta square alpha square. Okay, now put this value of d to psi by dx square is equal to alpha square d to psi by d zeta square in equation second. Say this is expression second, and therefore now put this value here, and we get this alpha square d to psi by d zeta square plus 2m by h bar square e minus 1/2 k x square, and x square is nothing but what? Zeta square divided by alpha square psi is equal to 0. Now this alpha divided by throughout alpha square, and therefore d to psi by d zeta square plus 2m by h bar square alpha square e minus 1/2 k zeta square by alpha square psi is equal to 0. Now this d to psi by d zeta square plus 2m e by h bar square alpha square minus 1/2 k multiplied with this. So this is a 1/2 2me divided by h bar square alpha raised to 4 k zeta square sine 2 cancel, and now put another value such that this is equal to say lambda, and solve this is equal to 1, and therefore this d2 sine d zeta square plus lambda minus zeta square sine is equal to 0. Say equation next 3. Now this differential equation, solution of this differential equation, so that is the psi of zeta, it must be acceptable values, and the range of this minus infinity to the plus infinity. Okay, and hence when psi of zeta acceptable one and zeta tends to infinity, then this alpha is lambda is very a small one, and then we can neglect it, and therefore this solution becomes d2 psi by d zeta square, okay, plus minus zeta square psi is equal to 0. Okay, again this type of the differential equation and solution of that should be asymptotic form, and the range of that asymptotic form is from the minus infinity to the plus infinity, and therefore this should be in the form of d2 psi by d zeta square plus h of zeta zeta square psi is equal to 0. A psi of zeta is equal to a h of zeta into a minus a zeta square by 2. Now solution of this differential equation is this a psi of zeta is equal to a h of zeta e raised to minus a zeta square by 2. So, okay, so this is a solution for this differential equation. Now find out the value of d2 psi. So this is the equation for this one, and then find out this dou psi zeta of dou zeta square, and from that d2 psi by d zeta square from this equation, and put in this value, okay, in equation 3, and therefore using this one the expression 3 becomes a e raised to minus zeta square by 2 into bracket h double dash zeta minus 2 zeta h of zeta plus lambda minus 1 h of zeta bracket completed is equal to 0. So this is a general function, and this is not equal to 0, means this equation should be 0, and hence this h double dash zeta, so this is the double derivative, h double derivative minus 2 zeta h of zeta plus a lambda minus 1 h of zeta is equal to 0. So this is the differential Hermite polynomial differential equation. To solve this solution differential equation by a power series. So that power series method we are already known in last semester using that MMP chapter. So this differential equation can be solved using Frobenius power series method. So Hermite polynomial, using the Hermite polynomial, the expression differential expression for Schrodinger's equation becomes this we consider as 1. So this h double prime. So this prime is a differentiation of h with respect to zeta. Okay, so h double prime minus 2 zeta h dash lambda minus 1 h is equal to 0. And this differential equation, Hermite polynomial differential equation, we are going to solve using a power series method. And so that detailed power series method we have seen in last semester in MMP paper. Okay, so differential equation. This is one of the method to find out the Hermite polynomial solution. And for that, consider this h of zeta is equal to summation m tends to 0 to infinite am zeta raised to 1, zeta raised to m. So this is expression 2. Now differentiate this with respect to zeta so that it becomes h dash, and we have now write this h dash of zeta is equal to a summation. So this is the am m zeta raised to m minus 1. So this is the m 1 to infinite. So this is the third one. Okay, the same one expression again we differentiate with respect to zeta, and therefore it becomes h prime double prime is equal to summation m tends to a 2 to infinite am as it is, m is also as it is. So this is the m minus 1 zeta raised to m minus 2. So this is expression 4. Say. Okay, now put this value of the h of zeta here, this h prime zeta is here and h double prime zeta is here, and therefore our equation becomes this a summation m to infinite am m minus 1 zeta raised to m minus 2, okay, minus 2 zeta into bracket minus 2 zeta into this summation m tends to 1 to infinite am zeta raised to m minus 1, and last term is, so this is the plus lambda minus 1 zeta, and value of zeta is what? So this is the summation m tends to 0 to infinite am zeta raised to m, okay, is equal to 0. Now this zeta is taking inside, we have this 2 a summation m tends to 0 to infinite am m, and 1 will cancel and this becomes zeta raised to m. Okay, these two are the remaining as the same, and then final expression we can write this. Okay, now here with m raised to 2 and zeta raised to m minus 2. Here it is the zeta raised to m. Here also the zeta raised to m, and therefore to become a common factor zeta raised to m, in first term we have to write m is replaced by m plus 2. Okay, and therefore this expression becomes m tends to 0 to infinite a m plus 2, this m plus 2, and this becomes m plus 1 zeta raised to m minus 2 a summation m tends to 0 to infinite am zeta raised to m plus lambda minus 1, this term as it is, lambda minus 1 summation m tends to 0 to infinite am zeta raised to m is equal to 0. Okay, now what we will do, this summation m tends to 0 to infinite, and zeta raised to m we have taken the common outside. Okay, and therefore this becomes a summation m tends to 0 to infinite into bracket. So this is the a m plus 2 m plus 1 minus 2am m plus lambda minus 1am and zeta raised to m is equal to 0. Okay, so now you consider here that each coefficient term is equal to 0, and therefore here we consider the coefficient of the zeta raised to m is equal to 0, means this bracketed term is equal to 0. This bracketed term is equal to 0, and therefore solve this for a m plus 2. Okay, and we can write here, so this a m plus 2 is equal to this becomes plus, so this is a 2m plus 1 minus lambda divided by m plus 2 m plus 1 am. So this is called the recurrence relation. Okay, so using this recurrence relation, if we know a0, put here the am is equal to a0, then we can find out, so this is the 1, if a0 is known, then a2, a4, a6, and if a1 is known, then we can find out a3, a5, a7 and all. So all even term of the power series and odd term of the power series can be find out, and from that this h of zeta psi can be written as in terms of this a0 plus a0 zeta this h0, so this h of zeta is equal to a0 plus 2 zeta square plus 4 zeta raised to 4 in all even powers plus a1 plus this a3 zeta 2 plus a5 zeta raised to 5 in all these terms. Okay, so this is a power series, and if you check this convergence of this power series, then we can easily show that this power series are a divergent one. Okay, and therefore there is a problem for asymptotic solution, and the solution has the infinite number of this power series, and this is the for a given value of lambda, for a given level of energy lambda, this solution of this is unacceptable. So, and that is in terms of zeta square by 2. So is equal to, so this is the zeta psi. So h of zeta psi is equal to a e raised to zeta square by 2. This is the unacceptable solution is getting, and this and very large number of series is there, and this can be avoided by considering the value of lambda such that after particular number this power series become a finite, and that can be possible if after m is equal to n, this power series becomes a finite number of terms, and therefore this recurrence relation becomes as a n plus 2 into bracket 2n plus 1 minus lambda divided by n plus 2 n plus 1 an is equal to 0. After that means this an not equal to 0, that means this term is equal to 0, transferring this into 0, and therefore 2n plus 1 minus lambda is equal to 0, and therefore lambda is equal to 2n plus 1. Okay, but in before we have known that the value of lambda is equal to 2e divided by h cross omega, and therefore this is 2e divided by h cross omega is equal to 2n plus 1, and therefore 2e is equal to 2n plus 1 h cross omega, and therefore e is equal to n plus 1 half h cross omega. Okay, so for different values of excited energy, in this En is equal to n plus 1 half h cross omega. So this is our eigen value for one dimensional harmonic oscillator. Now we are find out for energy for different values of n is equal to 0, 1, 2, 3 like that, and therefore if you put n is equal to 0, if you put n equal to 0, then so this En is equal to n plus 1 half h cross omega. Put n is equal to 0, we have the energy, ground state energy, and n is equal to 0, so this becomes 1 half h cross omega. So if n is equal to 2, then we get a 3 by 2 h cross omega. If n is equal to 3, we get a 5 by 2 h cross omega. N is equal to 4, we get a 7 by 2 h cross omega. N is equal to 4, we get so this 9 by 2 h cross omega, and the difference between this is h cross omega. This is h cross omega, so this is called an energy spectrum of h cross omega of harmonic oscillator. But in case of the classical result, energy spectrum for the harmonic oscillator is a continuous spectrum, so that energy E equal to 1 half a square. Okay, and that continuous in classical one we get a continuous energy spectrum, where in quantum mechanical treatment, so this is the discrete energy level. So this is the difference between a classical and quantum. Here this is the one part is completed, so that is the eigenvalue problem. In next part we are going to see corresponding wave function of this n is equal to 0 ground state wave function, then n is equal to 2 second excited state, n is equal to 3 next excited state, and what are the corresponding wave functions, and from that what is the probability of the finding the particles in this one, and correspondence principle, and then a parity. Okay, so this is the one part that we find out the eigenvalue of the one dimensional harmonic oscillator.